Welcome back. In this video, we're going to finish up Chapter 4 by doing Section 4.7, which is about systems of linear inequalities in two variables. So the overall plan is to see what exactly that is. What is a system of linear inequalities in two variables? What are the solutions like? And then how do you go about finding them? So first of all, what a system of linear inequalities looks like, an example would be this one. X plus 4y is greater than or equal to 10. And 3x minus 2y is less than 12. So what a system of linear inequalities is like, you can think of this as kind of a combination of section 3.4 and 4.1. In section 3.4, we had extended the idea of a solution to a linear equation in two variables, that is a line when you graph it, to a region, right? We graphed a line and then shaded one side or the other. In section 4.1, we looked at this system of equations in two variables, and we graphed two lines and looked for where they crossed. At least was the concept. Of course, realistically, we use substitution or elimination to get the work done, but that was a concept. Figure out where the two lines cross. In this section, we're kind of blending those two ideas. We have a couple of inequalities in two variables, like we might have seen in section 3.4. And in this section, we're looking for where the two solution regions for each of the individual inequalities overlap. So where we'll continue then is just to first decide whether a pair is a solution to a system or not. So for this first one, we've got the system x minus 5y is greater than 10, and 2x plus 3y is greater than negative 2. And first of all, we want to decide if 3 negative 1 is a solution. So let's look. We're going to do this by substituting in the xy pairs into our inequalities and see if we get true statements. So let's try the first point A then in the first inequality. So x, that's 3 minus 5 times negative 1 is greater than 10. Let's see if that's true. Okay, that's 3 plus 5. That's greater than 10. I was already getting ready to write no. That's 8. 8's not greater than 10, and so no. We don't even have to check the second one. You can if you want, but once we know that the point that we have isn't a solution to one of those inequalities, it's all over. It can't be a solution to the system because the points that would be solutions would have to be solutions to both of the inequalities. Okay, let's try 6 negative 3. So this will be point B. So x, that's 6 minus 5 times negative 3 greater than 10. 6 plus 15 greater than 10. That looks like 21 is greater than 10, so that works. Of course, that doesn't mean that this point is a solution to the entire system. We just know that it satisfies the first inequality. We should check and make sure that it fits the second inequality as well. So we'll have 2 times x was 6, plus 3 times y, which was negative 3. We want to know if that's bigger than negative 2 or not. 2 times 6 is 12. We have 12 minus 9. That's going to be 3, and 3 is bigger than negative 2. Since this point satisfies both of those inequalities, it's a solution to the entire system. How you solve a system of linear inequalities is by graphing. When we did systems of linear equations, we did graphing and then we did elimination and substitution. For this section, the only thing is graphing. So here's how it goes. The good news, the bad news. The good news is if you're pretty good at graphing lines, you're probably going to not have much trouble with this section. The bad news is if you're not that strong in graphing lines, you're probably going to have a tougher time with it because that's most of the work is graphing lines. Okay, so here we have y is less than 3x plus 2. I'm going to graph this first one. As you recall from chapter 3, since this is a strict less than, we're going to do it with a dashed line. Okay, so here the y-intercept is a 2, and the slope is a 3. So I will go up 1, 2, 3, and write 1 to get a second point on the line. Okay, and then we're going to connect the dots with a dashed line. Okay, now where I do this differently than you might see in the book or on other videos or your past teachers that you may have had is I'm not going to shade this now. I'm going to wait and shade it until later. And I'll tell you the reason why once we get there. But for now, I just want to know which side we would shade on if we were going to. So we're going to test the origin in that first inequality. So 0 is less than 3 times 0 plus 2. Is 0 less than 2? Yes. So that means that 0 is a solution to the first inequality, so that all the points on that side are. So I'm just going to remember by putting little arrows to remind me that I would be shading the right side of that if we were going to do the shading now. Okay, moving on, let's do the second one next. So the second one, I'm going to color that in blue. This one has got a greater than or equal to, and so I'm going to be graphing it with a solid line. The y-intercept here is -1, and then for the corresponding equation, it's minus x minus 1. The slope is -1, so we'll go down 1 and right 1. Okay, and then once again, we're going to connect the dots. Solid line because it's got the or equal to in it. And so now we want to figure out where we would shade the blue one. So again, if it's not passing through the origin, I like to test with the origin because the origin is easy to work with, right? So we'll have 0 is greater than or equal to minus 0 minus 1. 0 is greater than or equal to -1. That looks like it's true. So the origin makes a solution to this one, so we would shade above the blue line. The solution then to the entire system is going to be the region that makes up solutions to both of our individual inequalities. That would be to the right of the green and above the blue. So we're just going to shade that one. To the right of the green and above the blue. Okay, now I'll tell you why that's it. That's the end of it. There's no like interval notation or anything. Now I'll tell you why it is that I do the shading just at the end. The reason why is, although the book is able to present like nice coloring and things, if you were going to do this by hand, like on paper, then with a pencil, like just one color, make that slightly more careful, then let's say that we'd shade, okay, it was to the right of the green one, and then we drew the blue, what was blue, we would shade above that one. It looks kind of messy in my opinion, and it's harder to tell exactly what region is described. And if you're using just a single color like a pencil, it can be really hard to tell what is going on. That's the reason why I like to do the shading just at the end. Okay, so we will try more examples next. All right, let's try another one. This one, why don't you give it a try? Pause the video and try this one yourself, and then restart the video and see how you did. As a reminder, the overall plan would be to graph each individual line separately, that is, change the inequality to an equation, graph the line, paying attention to whether it should be dashed or solid, and take note of which side needs to be shaded for each one, and then at the end, we're going to decide which region should be shaded based on what is the overlap of the two individual regions. Okay, so let's try. Hopefully you've had a chance to work on this yourself. So we're going to have x plus y equals 2 for our first line. This has a y-intercept of 2 and an x-intercept at 2, 0. So let's go ahead and connect the dots. This one, both of these actually had an or equal to on them, and so we'll be drawing these using a straight line. Okay. And then I should check with the inequality to see whether 0 will make a solution or not. This doesn't pass through the origin, so it's safe to use the origin. 0 plus 0 is less than or equal to 2. Answer is yes, and so if we were going to shade, it'd be below this first line. Okay, so you can help me remember that. Okay, for the next one, y is greater than or equal to, but we're doing the equation now, equal to 2/3 x minus 1. I'm going to graph that line. It's got an or equal to, so again, we'll be using a solid line on that. And y-intercept is -1. And the slope is 2/3. So I'll go up to and write 3 to get a second point on the line. Okay. All right, so now for this one, we want to know for this line whether we should shade above or below it. So again, we're going to test the origin. So we'll have 0. Remember, you're testing the point in the inequality, not the equation. Of course, the origin won't be a solution to the equation because the line doesn't pass through the origin. We're testing it in the inequality. Okay, so 0 is greater than or equal to 2/3 of 0 minus 1. 2/3 of 0 is 0. 0 is greater than or equal to -1. Answer is yes. So we want to be above this line. Okay, so we're going to be below the first line we drew and above the second line we drew. So it's going to be this region right in here. Okay, and that's it. Okay, here's another one to try. Here we have y is greater than 3x minus 2 and y is less than -1. Take a minute, pause the video, try this one yourself, and restart the video and see how you did. Okay, so the first line will be y equals 3x minus 2. The y-intercept is at -2. We will go up 3 and right 1 to get a second point on the graph. Our original inequality had strictly less in it, not less than or equal. And so for that reason, I'll use a dashed line to make the graph because the line itself doesn't make it part of the solution. Okay, now we want to check the origin to see if that is a solution. 0 greater than 3 times 0 minus 2. That is okay. 0 is greater than -2. Answer is yes. So we will want to be above this blue line. All right, so now I need to try the next one. This one is interesting because it's a horizontal line. Y equals -1 is going to have y-intercept of -1 and is horizontal. Again, it's a strictly less, so we'll be using a dashed line to draw it. And then here, try the origin in this one. So putting the 0, 0 in for this, there's no place to put the x, that's okay. We'll just put in the y as needed. So y is 0. 0 is less than -1. 0 less than -1. Should be no, right? 0 is not less than -1. So the solution, the origin is not a solution. That means all the solutions are below this horizontal line. So the ones that are solutions to the overall system need to be above the dashed line that we drew first and below the dashed line we drew second. So this will be our region. Okay, here's one more to try. Again, this is basically as hard as these get now. We're graphing a line, we're paying attention to whether it should be solid or dashed, and we're making a little test and shading one side or the other. So it doesn't get a lot harder than that, at least for now. All right, so here we've got 3x minus 2y equals 12. This one is good for using the intercepts. When x is 0, y should be -6. When y is 0, x will be 4. So we'll have 4, 0, and 0, -6 as points. This first line had an or equal to in it. They actually both do. So we'll be using a solid line for both. And then check the origin. 3 times 0 minus 2 times 0 is greater than or equal to, zeros on the brain, 12. So 0 minus 0 greater than or equal to 12. 0 is not greater than or equal to 12. The origin fails, so we're going to want to shade below this first slanted line. Okay, now we're going to go with the second one. y equals 3/2 x plus 1. For this one, the y-intercept is 3. Sorry, I lied. The y-intercept is 1. The slope is 3/2. So we will go up 3 and right 2. And then we're going to shade this one with, do the line with a solid line because of the or equal to. That one's parallel to the first one. That's pretty neat. For the test, we'll check the origin again. So we want to see if the origin is a solution. So 0 greater than or equal to 3/2 of 0 plus 1. Is 0 greater than or equal to 1? Answer is no. Since the origin isn't a solution, there are no solutions on that side of this line. That means they have to all be on the other side. So this one is interesting. The two lines are parallel. For the first one, the solutions were below the line. For the second one, the solutions are above the line. So overall, this one has no solution. Why? Because there's no points that are in common to both of the solution sets for the linear inequalities themselves. So there's no solution. When we're finding the solutions, we want to find the points that belong to the first one and the second one. So make sure that you know the difference there between and or in this context, and that will help you. So this one, there's just no solution, and that's there's nothing to shade for that. Okay. All right, we have one more. And then a word problem. Okay, so y is greater than or equal to 2x plus 1. The corresponding equation, y equals 2x plus 1. There, the y-intercept is 1, slope's 2. Solid line for this one because it's got an or equal to in it. Okay, and then which side shall I shade? So let's check that. This guy doesn't pass through the origin, so once again, we can test with the origin. 0 greater than or equal to 2 times 0 plus 1. 0 greater than or equal to 1. Answer is no. So none of the points on the right side will make solutions. So that means that all the solutions have to be on the left side or upside, depending on how you want to look at it. Okay, for the next one, we have negative 2x plus y equals negative 4 as a line. And then for this one, it'll be kind of nice to use the intercepts because it's in kind of general form. When x is 0, y will be negative 4. When y is 0, x will be 2. Okay, so we have 2, 0, and 0, negative 4. This one looks kind of parallel to the first one. We're going to be using a dashed line this time. And again, we want to check the origin, see if the origin makes a solution to this inequality. Negative 2 times 0 plus 0, is that greater than negative 4? We want to know. 0 plus 0 greater than negative 4, is 0 greater than negative 4? And the answer is yes. So we want all the points that are above this line as solutions to this inequality. So again, here's where we've got to be careful about and versus or. For this one, we want all the points that are solutions to the first inequality and the second inequality. So we have to think about it for a little minute. This point, is that above the first line and above the second line? Yes, it is. This one would be an example of a solution. This point right here, let me make this one a different color so we can talk about it. This point right here, 1, 1, that's a solution to the dashed line inequality, but not to the first one we drew. We want the points that are solutions to both. So that would be all of the points above the first line. We want the points that satisfy the first inequality and the second inequality. Okay, So that takes that. So a couple of special cases there. We're going to finish the section by looking at a story problem. Admittedly, some of the story problems in our textbook are kind of contrived. That is not so realistic, but we need to do at least one. So let's do it. So the story here, it says Mark is increasing his exercise routine by running and walking at least 4 miles each day. His goal is to burn a minimum of 1,500 calories from this exercise. Walking burns 270 calories per mile and running 650 calories. We're to write a system of inequalities, and then we'll graph it and then answer a couple of questions about it. So first thing to do is to work on a graph. So for the horizontal axis, we're going to make that be, we're doing walking and running. Okay, so the horizontal axis is minutes, right? So the horizontal axis will be the number of minutes spent running. And the y-axis will be the minutes walking. Okay, we're trying to figure out how many minutes of running and walking he should do. Or is it miles? Okay, no, the inputs are miles, not minutes. I had minutes in there for some reason. Okay. All right, so miles walking on the y-axis, miles running on the x-axis. X will be the miles spent running, y will be the miles spent walking. Okay, so now we need to start making up some inequalities for this. First of all, he's going to run and walk at least 4 miles each day. So I don't think that means that he's running 4 and walking 4. I think that means together he is to run and walk all together at least 4 miles. So let's make x plus y at least would be greater than or equal to 4. So that's our first inequality. The second one is he wants to burn a minimum of 1,500 calories each from this exercise. So it would be okay if it's more, right? If he wants to burn at least the 1,500 calories. Walking burns 270 calories per mile. So we'll have 270 y for the calories burnt walking. And running 650 calories a mile. So we'll have 650x. And that's the total calories burned. That needs to be at least the 1,500 total calories that he wishes to burn. So that's going to be our system of inequalities. The first one, x plus y being at least 4, we can go ahead and draw that on now. I'm going to make this one red. And it stands out. For that one, if you think about it, the two intercepts are going to be at 0, 4, and 4, 0. He's supposed to be doing 4 miles of running and walking together. If he does no running, he's doing 4 walking. If he's doing no walking, he's doing 4 running. Okay, so that's going to be our first inequality. And we want it to be greater than or equal to 4. If you put 0 into this first inequality, 0 plus 0 greater than or equal to 4. No, that's false. So we want to be above this red line. Okay, so let's just try to remember that we're above that red line. For the second inequality, it's going to be a good idea to try to simplify this inequality down some before we attempt to graph it. So let's do that first. I can see, first of all, that all the numbers here are divisible by 10. So let me divide through by 10. So we'll have 27y plus 65x is greater than or equal to 150. And then look at the corresponding equations for this. That'll be 27y plus 65x equals 150. Okay, so then for this, we'll graph this using the intercepts. Okay, when x is 0 and when y is 0. Okay, when x is 0, we'll have 27y equals 150, so that y is 150 over 27. And that's not going to come out clean. That's Okay, a lot of times with story problems, they're not gonna, this is about 5.6. We'll just round to the nearest tenth for our answers on this one. For the other one, when y is 0, we'll have 65x is equal to 150, so that x is 150 on 65. Okay, and that's about 2.3 or so. Again, I've rounded to the nearest tenth here just for convenience. Okay, so then let's put on these points. So 5.6, when x is 0, we should be at 5.6. And then when x is 2.3, y will be 0. And so let's connect the dots again. There we are. Okay, so again, here we would like the amount of calories burned to be at least the 1500. So we want greater than or equal. So that means that our solutions will be all of the points that are above both the red and the blue. Here it wasn't stated, but I think we can assume that time's positive. So that's why I've just have both of our inequalities drawn in quadrant 1. We're not going to have negative time after all. So this will be our whole solution region right here. I'll leave it to you to figure out where these 2 points, where these 2 lines intersect. Okay, we've graphed it. Could he meet his goal by walking 3 miles and running 1? So walking 3 and running 1, that doesn't look like he could. It's not part of our yellow shaded part. Walking 3 and running 1 wouldn't do it, so I would say no. Okay, how about walking 2 and running 2? So that looks like it probably could. That is above both of those lines, so I would say yes. All right, so that takes us to the end of section 4.7 and the end of this chapter, actually. Let me know if you have any questions, and then have a great day.